So in this video, I will go through Springleaf data. It was a competition on Kaggle. In that competition, the competitors were to predict whether a client will respond to direct mail offer provided by Springleaf. So presumably we will have some features about client, some features about offer, and we will need to predict 1 if he will respond and 0 if he will not. So let's start. We'll first import some libraries in here, define some functions. It's not very interesting. And finally, let's load the data and train and test one and do a little bit of data overview. So the first thing we want to know about our data is the shapes of data tables. So let's print train shape and test shape. What we see here, we have 150,000 objects, both in train and test sets, and about 2,000 features in both train and test. And what we see more than that, we have one more feature in train. And I assume it's just a target concatenated to the train. So we should just keep it in mind and be careful and drop this column when we fit our models. So let's examine train and test. So let's use this function head to print several rows of both. We see here we have ID column, and what's interesting here is that see, in train we have values 2, 4, 5, 7, and in test we have 1, 3, 6, 9, and it seems like they are not overlapping. And I suppose the generation process was as following. So the organizers created a huge data set with 300,000 rows, and then they sampled at random rows for the train and for the test. And that is basically how we get this train and test, and we have this column ID. It is a row indexed in this original huge file. Then we have something categorical, then something numeric, again categorical, then something that can be numeric or binary, but you see it has a decimal part, so I don't know why. Then some very strange values in here, and again something categorical, and actually we have a lot of in between. And yeah, we have target as the last column of the train set. So let's move on. Probably another thing we want to check is whether we have not numbers in our data set, like nonce values. And we can do it in several ways. And one way, let's compute how many nonce are there for each object, for each row. So this is actually what we do here, and we print only first 15 values, I mean, with the values for the first 15 rows. And so the row 0 has 25 nonce, row 1 has 19 nonce, and so on. But what's interesting here, 6 rows have 24 nonce. And well, it doesn't look like we got it at random. It's really unlikely to have this at random. So my hypothesis could be that the row order has some structure, so it's not the rows are not shuffled, and that is why we have this kind of pattern. And that means that we probably could use row index as another feature for our classifier. So yeah, that is it. And the same thing we can do with columns. So for each column, let's compute how many nonce are there in each column. And we see that ID has 0 nonce, then some zeros, and then we see that a lot of columns have the same 56 nonce. And that is, again, something really strange. So either every column will have 56 nonce, and so it's not a magic, it's probably just how the things go. But if we know that there are a lot of columns and every column have well, different number of nonce, then it's really unlikely to have a lot of columns to get near to each other in a data set with the same number of nonce. So probably our hypothesis could be here that the column order is not random. So we could probably investigate this. So we have about 2,000 columns in this data, and it's really huge number of columns, and it's really hard to use, hard to work with this data set. And basically we don't have any names, so the data is anonymized. And as I told you, the best thing we can do, the first thing we can do is to determine the types of the data. So we will do it here. So we will first concatenate, train, and test in a huge data frame like the organizers had. It will have 300,000 rows. And then we will first use an unique function to determine how many unique values each column has. And basically, here we print several values of what we found, and it seems like there are 5 columns that have only one unique number, so we can drop them. Basically what we have here, we just find them in this line, and then we drop them. So next, we want to remove duplicated features. We first, for convenience, fill not numbers with something that we can find easily later. And then we do the following. So we create another data frame of size, of a similar shape as a train set. What we do, we take a column from train set, we apply a label encoder, as we discussed in a previous video, and we basically store it in this new train set. So basically we get another data frame, which is train, but label encoded train set. And having this data frame, we can easily find duplicated features. We just start iterating the features with 2 iterators. Basically, one is fixed, and the second one goes from the next feature to the end. And then we try to compare the columns, the 2 columns that we're standing at, right? And if they're element-wise the same, then we have duplicated columns. And basically, that is how we fill up this dictionary of duplicated columns. We see it here. So we found that variable 9 is duplicate of variable 8. And variable 18, again, is duplicate of variable 8, and so on. So we have really a lot of duplicates in here. So this loop, it took some time, so I prefer to dump the results to the disk so we can easily restore them. So I do it here, and then I basically drop those columns that we found from the train test data frame. So yeah, in the second video we will go through some features and do some work with the data set.